Good morning, students. Let us start the class. We have been discussing Shannon's encoding algorithm till now, and we had seen some examples also. Today, we will see the next method of encoding, that is called Shannon-Fano algorithm. This is a slightly easier method when compared to the earlier discussion of Shannon's algorithm. So, for your test, until whatever I covered for the previous class, it will be there. Excluding this Shannon-Fano algorithm, whatever I'm going to discuss today, till the Shannon's encoding algorithm, whatever we discussed till the previous class, that will be there for your test. And today I'll be posting the question bank in the Google class. I hope the notes is already downloaded by all of you, because I had uploaded the notes long back in the Google class. I hope you are going through it. So the complete first module, and in the second module up to the Shannon's encoding algorithm, that much is the syllabus for the first internal test. Fine, let me start with the Shannon-Fano algorithm. As I told you, this is easier than the earlier algorithm. So this algorithm or this encoding procedure contains the following steps. The symbols are arranged in the decreasing order of their probabilities. This is the same as that of the earlier Shannon's algorithm. Next, the symbols are divided into two groups such that the sum of probabilities in each group is approximately equal. That means the total symbols, when they are arranged in the decreasing order, basically we divide them into two sets. Approximately each set must have the sum of the probability equal to 0.5. Because anyhow, the sum of all the probabilities is anyhow going to be unity. So this has to be each group approximately. We cannot exactly get half everywhere there. Approximately it has to be 0.5. Now, when this is made as two distinct groups, immediately we can allocate two codes for each group. One is 0, one is 1. Or one is 1, one is 0. That way we can immediately allocate. And in the same way we go on further. Means again this particular group we divide it into another two groups, again 0.25 approximately, and then we give the code 0001, then we give the code 1011, and that way we go on. So there is no computation of ni here. We had calculated ni earlier, and then we had calculated a fraction, and the fraction we converted into binary. And from the binary fraction, we discarded the integer part, we took the fractional part of the binary. That was our code. Here in Shannon's Fano algorithm, the procedure is really quite easy. In the sense, no need of calculating ni, and no need of computing the fraction also, no need of conversion to binary. All of the procedures are completely non-existing here. So that is the procedure. We are anyhow going to see the examples. It will be very clear to you. Now the third one is all the symbols in the first group are designated by 1 and the other group by 0, as I told you. But the first one also can be 0, next one also can be 1. It does not matter much there. Then each group is divided into two subgroups so as to have approximately equal sum of probabilities, and the process is repeated. And the process is continued until no further subdivision is possible. Let us see an exercise. Consider an 8-alphabet source with alphabets A to H having probabilities as 0.3, 0.2, 0.15, 0.12, 0.02, 0.07, 0.1, 0.04. Construct a binary code using Shannon-Fano procedure and find the code efficiency and redundancy. Construct the code tree. This I am going to show you later on how to construct a code tree. Also find the probabilities of zeros and ones in the code. This also I am going to show you how we are going to compute these things. So let us try to solve this exercise now. Initially what we have to do, we have to arrange. There are totally now A, B, C, D, E, F, G, H. Totally 8 symbols are given, right? You can see here A to H, A, B, C, D, E, F, G, H. Totally 8 symbols or 8 alphabets are there. We have to arrange them in the decreasing order. A is having 0.3, then B is having 0.2, C is having 0.15, D 0.12, G is 0.1, F is 0.07, H is 0.04, E is 0.02. So we have arranged the symbols in the decreasing order. Now look at this. A and B together is 0.5. Naturally, all the other, when you sum up them together, it will become 0.5 because the net probability of all the 8 symbols is unity itself. So immediately what we can do now, A is 0.3, B is 0.2, together we will group them. Then all of the other things we will group them. Now we will assign the binary digit 1 to the first group, binary digit 0 to the second group. We already have started the encoding now, right? Without any further calculation, we have already started the encoding just by dividing the symbols into 2 distinct groups. Next, what we will do, the first group, it is containing only 2, A and B. We will further divide them as separate 0.3, separate 0.2. Now you can see, for 0.3 we will again allocate 1, again we will allocate 0. Now, the only thing we have to be careful here is, if we assign 1 in the beginning for the first group, if we assign 0 in the later on stage for the next group, we have to follow the same procedure again and again. That means again start with 1, then 0. Again start with 1, then 0. We have to have the same methodology. Otherwise, we may not get the instantaneous codes. What is meant by an instantaneous code, I am going to tell you later on. But let us follow the same procedure again. That means the first group divide into 2 distinct groups. Again allocate 1, again allocate 0. Now the second group which is there, again divide it into 2 distinct groups. Approximately we should get 0.25, 0.25. Now you can see 0.15 plus 0.12 is 0.27, which means this itself became another group. Other thing is obviously 0.23. 0.1, 0.07, 0.04, 0.02 is totally 0.23. So for this first group, again we will allocate binary 1, and for the second group we will allocate binary 0. This is the second stage of encoding. Next, anyhow, for the first group in the beginning, for A and B, already encoding is done. You can see here 1, 1 and 1, 0. That encoding is already complete because we cannot divide the group further. Now in the case of this second stage, you can see that C and D are together. Again we divide them into 2. 0.15, 0.12 is like that, C and D. Again we will allocate 1 and 0. So the encoding procedure for C and D are complete. 0, 1, 1 and 0, 1, 0. We cannot divide them further. Next left out is this GFHE. Again in this GFHE, total is now 0.25, right? In the first stage it is 0.5 and 0.5. Next stage it will be 0.25 and 0.25. Next stage will be 0.125 and 0.125, because we are dividing the group into 50% each every time. So in the first stage it is 0.5 and 0.5. Please remember that. In the second stage it is 0.25, 0.25, 0.25, 0.25. In the third stage, if it remains, everywhere it will be 0.125, 0.125, 0.125, 0.125. Now in the first case, as G itself is 0.1, let us make it as one group itself, because if we add it now, it may become 0.17, right? We wanted to have 0.125. Now this is 0.17, which is slightly larger. So we can keep G itself as it is, as 0.1. That the remaining is one group. So for G we will allocate 1, for the other group we will allocate 0, 0, 0. Next again, last one is FHE. We will separate this F separate and HE separate. F is 0.07, HE is 0.04, 0.02. So this is now 0.7 and 0.07 and 0.06. Now for F we will allocate 1, and for H and E separately we will allocate 1 and 0. That means the encoding is now complete. Without any further calculation, It's a very simple procedure where encoding is fully complete. So this is a value addition to the regular Shannon's encoding. Now you may think, if this is so easy, why was there that Shannon encoding? We have to give credit to Shannon. He first thought that way. Okay. Later on, Fano added some more methodology to the Shannon's algorithm. And that is how this became Shannon's Fano algorithm. That's how it became simple. We have to always give a credit to the first person who is an innovator there. Shannon was the innovator in the beginning. Later on, all these concepts can be gradually improvised by the succeeding scientists. Let me sip water now. So that is how Shannon's Fano's algorithm came into picture, and this is quite simple. Now we have the final code. For A it is 1 1, for B it is 1 0, for C it is 0 1 1, D it is 0 1 0, G is 0 0 1, F is 0 0 0 1, H is 0 0 0 0 1, and E is 0 0 0 0 0. Now this is how the final coding is done. So hence the codes are, you can see here. Let me slightly reduce the zoom ratio, or is it fine? It is fine. Okay. A is 1 1, B is 1 0, C is 0 1 1, 0 1 0, 0 0 1, 0 0 0 1, 0 0 0 0 1, 0 0 0 0 0. Now, one point I want to stress here is, initially we started with 1, then we gave 0 to the second group, right? Now you can do the reverse also. You can start with the 0 here, then you can allocate 1 here. That way you can go on. So what it will become is, if at all you follow that procedure, A will become 0 0, B will become 0 1, C will become 1 0 0, D will become 1 0 1, G will become 1 1 0, F will become 1 1 1 0, H will become 1 1 1 1 0, and E will become 1 1 1 1 1. That also is a good coding only. That also is one more way of implementing the Shannon's Fano algorithm. But which one will be better now? Can any of you tell me now? Starting with 1 and 0, is it better? Or starting with 0 and 1, is it better? One of you have to tell me now, either in the chat box or you can unmute and tell me. Okay, Kuldeep is saying starting with 1 is better. Tell me why. You can unmute and tell me.
Sir, I think we can save power or...
Right. Excellent, Kuldeep. Right. We can save power. Here it is 1 1 and 1 0, and then 0 1 1 0 1 0. You can go on. Lengthiest code for E is 0 0 0 0 0. Now, if at all we go for the reverse case, this will be 0 0, this will be 0 1, and for E it will be 1 1 1 1 1. That means there will be 5 pulses of 1 each. In the first case, for E, there will be 5 pulses of 0 each. That means even though there is a signal is there, signal will not be having the voltage there because it is 0. But if we allocate 1 for this E, then it will be having 5 pulses with supply voltage there. The lengthiest code will be having supply voltage there. Whereas in this particular case, in the first case, it is all 0 there. That means choosing 1 first and 0 next, we are going to save a lot of power. We are going to save a lot of power in everything as such. Everything in the sense, if at all we have a digital circuitry and we are going to use a transmitter there, the transmitter will have a digital circuitry there. We will have multiplexers there, and we will have memory there. Everywhere we are going to save a lot of power. Ultimately, the present generation is We want to have a lighter equipment. We want to have a high speed equipment. We want to have a high memory equipment. We want to have a low power equipment. And we want to have a low cost equipment also. And that is all being met to some extent now. That means we can save power. Now I am discussing the code which is having only 2 bits and 3 bits and 4 bits and 5 bits. We may have lengthier codes. When the number of symbols are more, we can have much lengthier codes. Now think about the situation where if the number of ones is more, then there is going to be more power. In this particular case, if the number of 0 is more, we are going to save power. Exactly, that is the answer. That is why this itself is better. Even though I told you that there are 2 approaches, this approach itself is better. Let me continue now. Let us calculate the source entropy. Source entropy is given by h of s is summation of I equals 1 to 8 of pi into Lg of 1 over pi. This you are already familiar. And I will show you the answer now. The source entropy is 2.6627 bits per symbol. Now, let us calculate the other things. The average code word length per symbol. In the last exercise, we had given a different notation for that as h cap. The same thing here we are writing it as L. When it comes to Shannon Fano, only the notation changes, but the procedure is same. Procedure is summation of I equals 1 to 8 of NIPI. Why I am choosing both the notations is because different textbooks use different types of notations. So I thought in the earlier exercise, let me use that h cap of n, and here let me use L. L is nothing but average code word length per symbol. That is summation of I equals 1 to 8 of Ni into Pi. Now we know that A is 2 bits and B is 2 bits, then C is 3 bits, that way it goes on. And we know the probability of each symbol there. When we find out, ultimately it is 2.69 bits per symbol. Now you can see source entropy is 2.6627 bits per symbol, whereas the average code word length per symbol is given by 2.69 bits per symbol. So the efficiency is nothing but 2.6627 divided by 2.69. That is, efficiency is 98.98%. You can really admire this algorithm. When compared to our earlier Shannon's algorithm, the Shannon-Fano algorithm's efficiency is larger and the effort is lesser. Now, redundancy is R eta C is nothing but 1 minus 0.9898 equals 1.02%. Redundancy is only 1%. Efficiency is nearly 99%. That way we should say that this is a very good coding algorithm with the least effort. Now let us see how to write the code tree, and I will show you the code tree and I will tell you what is the use of the code tree. We can write the code tree like this now. See, we have source. From source, we will start with the, let us say, right hand side 1, left hand side 0. Now when I write 1 again, next one more 1 is A, one more 0 is B, because the code for A was 1 1, code for B is 1 0. Next, when we start with the second group, that is 0, again we will have 1 and we will have 0. And we have to continue like that. Again one more 1, one more 0. When we reach with 0 1 1, it is C. For 0 1 0, it is D. Next, when we have 0 0 1, it is G. 0 0 0 1 is F. 0 0 0 0 1 is H. 0 0 0 0 0 is E. So, what can be the use of this particular code tree if it is written in a graphical fashion? Let me annotate this now. Now, can anyone tell me what can be the use of this particular code tree? Why should we write this code tree for each symbol? What may be the use of this graphical representation? Can anyone tell me? Either you unmute or you put it in the chat box. No answer. Nobody gave me answer. Fine, I'll give the answer. The answer is all our electronics is always with an embedded software, right? Any electronic equipment is not purely hardware. Always there is a software. And in the software, let us say the transmitter also has got a software, receiver also has got a software. In the software, it has a memory. And in the memory, the codes have to be stored. Now we are going to go for a variable length code. It is not a fixed length code. ASCII code is a fixed length code. EBCDIC is a fixed length code. Whereas Morse code was a variable code. Now the Shannon Fano code is also a variable code. Which means the code has to be stored in the memory of the transmitter and it has to be stored in the memory of the receiver as well. Whenever this code is transmitted from the transmitter to the receiver, at the receiving side, it has to decode it. And at the transmitting side, the transmitter has to encode it. For encoding, from where it will take the codes for each symbol from the memory. Now, how do we organize these codes inside the memory? We can easily write a program for this code tree itself. Easily we can write a small C program or any program, microcontroller program, microprocessor program, any assembly level program. We can easily write a software program for this code itself. And we can store that software program in the transmitter's memory, in the receiver's memory, in the embedded operating system there. Every electronic system is now having a embedded software. Now, you may ask, why should we store it in a software? Why can't we permanently store it in a ROM? We need not store it in a ROM permanently as a physical memory because then the flexibility of changing the code will be lost. Anytime we want to enhance the efficiency of the system, we can have a different coding procedure and we can always upgrade the system with the new set of codes. So at that time, we can simply change this program itself, which is resident in the operating system. That is enough. So when the codes are represented as a tree structure or a graphical approach, then we can easily put this tree diagram itself into MATLAB. If we put this tree diagram into MATLAB, MATLAB can immediately generate a Verilog code. Nowadays, MATLAB is so powerful. If you give a block level Simulink model, you can actually obtain a Verilog code. And that Verilog code can be directly synthesized and it can be downloaded into the FPGA kit. That way MATLAB is so powerful now. So this tree structure, it can be easily represented by means of a MATLAB program and later on it can be used for any of our enhancement purposes. That is the purpose of writing all these things in the graphical fashion. In fact, we are the hardware engineers, we are going to design the hardware systems. For the hardware systems, the software is written by computer science engineers. In fact, electronics, computer science, electrical and mechanical, they all go hand in hand for any given product. For example, I have a cell phone with me now. The cell phone's complete body is going to be designed by a mechanical engineer. Its circuitry is going to be designed by an electronics engineer. And its operating system is going to be designed by a computer science engineer. And its charging circuitry and its battery related parts are going to be taken care of by an electrical engineer. So, the mobile phone's complete functionality is not just electronics. It has got the other branches contribution as well. So now, a computer science engineer is going to study a subject called graph theory and combinatorics. Then they are going to study another subject called algorithms and system programming. Many such related courses they are going to study. Now, it is their job to represent the graphical things in the other way, to store it into the memory of the electronic system by means of the respective software or the operating system. That is where I mentioned that computer science engineer is going to study a separate course called graph theory and combinatorics, where everything can be represented as graph and the graph can be gradually converted into a code. That is the idea. That is why in this exercise we are writing the code tree. Let me proceed further. Now the last question asked is, in this exercise the last question asked is, students are waiting in the lobby. Fine, I am admitting. Probability of zeros and ones in the code are given by P of 0. I am writing capital P. Okay, P of 0 is 1 over L into summation of Q equals 1 to Q of number of zeros in the code for that particular message into Pi. Please remember this. We want to find out the probability of zeros and ones occurring in the given code, so that we will know how efficient our code is in terms of zeros and ones. I am going to show you later on the data. So P of 0 is L, we have already found out. So 1 over L into summation of I equals 1 to Q of number of zeros in the code for a given symbol into its probability. For example, in the code for A, there are no number of zeros, there is only 2 ones. In the code for B, it is 1 and 0. In the code for C, number of ones is 1, number of ones is 2, number of zeros is 1. In the code for D, number of ones is 1, number of zeros is 2. That is what we are going to compute here. We are going to compute P of 0 and P of 1. P of 1, again the same procedure, 1 over L into summation of I equals 1 to Q, number of ones in the code for the given message into Pi. Anyhow, in this example, we are not considering a message, we are considering a symbol or alphabet. So that way, actually message is again a combination of symbols. Message can be always called as a sequence also, and message can be always called as a block size also. Anyway, now P of 0, as per this defined formula, we get P of 0 as 0.4684. Now P of 1 we get 0.5316. Obviously, P of 1 will be 1 minus that of P of 0, because in the code only 0 and 1 are existing, right? There is nothing called a tri-state here. Either 0 or 1. So actually you need not compute this P of 1 again with this procedure. We can simply put 1 minus 0.4684, that is 0.5316. Means a code will be always really efficient when the zeros and ones are of equal probability. You can see that ones are occurring for nearly 53% time and zeros are occurring for nearly 47% time, which means this is actually a good code. If 1 and 0 are occurring 50%, then it is actually a good code. Of course, if we put 1 first and then 0 next when we do the grouping, then the lengthiest code will be always having 0. That is also better for us because we are going to conserve power there. But we cannot completely eradicate ones, right? We cannot have only zeros in the codes. We should have both zeros and ones. That is why in the beginning we use ones, later on we use zeros. Now you can see why the probability of 1 and 0 is computed, because we want to find out if it is 50-50, then it is a better code as such. Obviously, P of 0 is 1 minus P of 1, as I have told you. Now I am going to show the next exercise and I will give you nearly 5 minutes time. You complete the first part only. Remaining part, I will show you the solution. The first part of dividing them into groups and encoding, you only have to do. Quickly take your notebook, take your pen, and I am going to show you the exercise. You are going to solve it. Okay, this is what I am showing you. An information source produces sequences of independent symbols having the following probabilities: A, B, C, D, E, F, G, 0.33, 0.25, 0.15, 0.12, 0.08, 0.04, 0.03. Now, construct a binary code using Shannon Fano procedure and find its efficiency and redundancy. I will not give you 5 minutes, I will give you only 3 minutes. Actually, 3 minutes is sufficient. Why? Because already they are arranged in the decreasing order. You can see here, A, B, C, D, E, F, G, it is already in the decreasing order of probability. You can straight away write it as A, B, C, D, E, F, G and then divide it into subgroups, and within the next 3 minutes, either you unmute and tell me the answer or you put it in the chat box. Your time starts now. There are 33 students in the class and only 3 are responding. Kuldeep, Indrajit and Manideep. Only these 3 students have responded. That means the remaining 30 students are simply logging in and not doing anything. Is it so? It is such a simple exercise. For that simple exercise, I gave more than 3 minutes time and you people are not working it out. I appreciate Kuldeep, Indrajit and Manideep for your efforts. But okay, now Chandramohan has responded. Fine, at least 4 are responding. That means we are finding out the efficiency of the code. I should find out the efficiency of the class. Efficiency of the class is 4 by 33. Very poor efficiency. It is such a simple procedure, and if you cannot take a notebook and pen, if you cannot make an effort there, I really feel that for the classes which I am taking, only 4 or 5 students are responding. For other students, no need of a class also, no? Which means all of you are already geniuses, right? You don't need a class also, right? You can read the textbook on your own and you can become engineers directly, right? Is that so? If that is so, I don't have to teach you, right? I can keep teaching only Indrajit, Kuldeep, Manideep and Chandramohan. I need not teach the other students at all because you are too much brilliant than me, right? That is what I should presume. From the next class onwards, the students who are logging in, if you do not put any least effort also for whatever I am telling here, then I should simply remove you from the meeting, right? I should simply remove you from the meeting because you are simply logging in and doing nothing. In that case, you are more brilliant than me. You can read textbook on your own. You can read these notes also on your own. You don't need my teaching. I am stupid and you are intelligent. I should come to that conclusion. Yes or no? You honestly touch your heart and ask yourselves. If you don't study at least 1 hour per day, and if you don't revise the topics which teachers are teaching you every day, then you are into deep trouble. You are into deep trouble because we are going to finish our portions as early as possible because it is all online now. We are in a pressure to finish our syllabus earlier. So, we will be going in a quicker speed from now on. For the first module, I went really very slow. For the second and third modules, all of us, all the teachers will be picking up speed because we have to complete the portions. Now, your load will increase if you don't involve in the class and if you don't at least do this small thing which I am asking you to do, then you will not understand. If you don't regularly work out all these things, you will not understand. And you are not a machine that you will memorize everything. You are not a robot that you will memorize everything. The other students will have real trouble. Later on, don't blame us. And again, please understand, next semester, the placement efforts are going to happen. And there will be technical companies coming, core companies coming, technical interviews will happen. And then, if you do not understand this concept and if you do not answer the questions, ask yourself how you are going to be placed in companies. Ask yourselves, if you ignore the studies, if you remain in a comfort zone, then you will be into deep trouble. That is my warning to you. This is not my suggestion or this is not my advice. It is my warning to you. Ultimately, it is your fate then. If you ignore my warning and suggestion also, then it is your fate. We cannot help it. Anyway, let me not increase my sermon now. Already some of you may be angry on me. So let it be. That is also your own choice. To become angry or sad is your own choice. I am doing my duty. That's all. So let me appreciate Kuldeep and Indrajit. Kuldeep has given the answer 11100100100001 00001 and 00000. And Indrajit has given the answer 11100100100001 and 0000000. Indrajit, by mistake, he might have put one additional 0. There will not be 6 zeros there, there will be 5 zeros only. And Indrajit has given the efficiency as 97.7%, Manideep has given 97.7%, and Chandramohan has given the answer 1110010001 0001 00001 00000. And Kuldeep also gave the answer that the efficiency is 97.75%. Excellent. I appreciate these 4 students who are at least responding to a stupid teacher's query, because teachers are stupid. All you students are really very intelligent, right? Only me, Kuldeep, Chandramohan, Manideep and Indrajit are stupid people. All other students are really very intelligent people, because you can simply mentally do all this work and you can simply understand everything, right? You don't require any teacher's help also, but you simply log into the class for what? I don't understand that. Anyhow, a Google link form I am going to put it into the Google class. Even if the people who do not come to the class also are going to get this Google link and they are going to enter their attendance there. So if the other people are simply logging in for the sake of fun, I don't know what for, if you do not work out the exercises. Fine. Let me go on. This is the binary code. I will come to the next part of this problem later on, because I cannot complete the other thing. There is a second part called construct a ternary code using the same procedure and find its efficiency and redundancy. In the next class, I will tell you what is the meaning of the ternary code. But let me show you the answer now. Answer is A and B are one group, C, D, E, F, G are another group. Approximately it has to be 0.5 and 0.5. So it is 1 and 0 here. Then again divide A and B separately, then divide C separately, D, E, F, G separately. Like that you go on. Now you can see 1, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. That means all the students have given the correct answers. And the codes are, I have already shown you. H of S is computed as 2.4345 bits per symbol, and L is computed 2.49 minutes per symbol. We can have a notation as binary units or binits also. So the efficiency is 2.49 divided by 2.4345 divided by 2.49. That is 97.77%, and the redundancy is 1 minus 0.9777, that is 2.23%. Compared to the previous code, this code is not as that efficient, because in the previous code we got 99% efficiency, 1% redundancy. Here we are getting 2.2% redundancy. That way the previous code was better code. But we cannot change it as such, because it is dependent on the probabilities of the symbols as well. We cannot change it as such. In the next class, let me discuss about what is the meaning of the ternary code and what is its usage in the communication system. Now, as it is already time up, I am going to end this class. See you in the next class. In the Google class, today I am going to upload the question bank for the first test, and I expect that all the other students also put their efforts in understanding the first module and the second module, whatever I am discussing now, and they will perform better in the first test. At least that is going to be my hope. At least let that hope be positive. At least let me believe the section A students that this particular teachers, this expectation also, let it be fulfilled. At least from now on, you study the subject thoroughly and you still have time and work out all these exercises and